Okay, so suppose you have a two-dimensional function. Let's call it u. U is a function of, let's say, x and y. It's a two-dimensional function. And partial derivative of y with respect to x is defined in the following way. Partial derivative. dy, this is how we write partial derivative. Dy dx is just the limit when delta x goes to 0, y x plus delta x, u x plus delta x minus u of x y divided by delta x. This is a definition of the partial derivative of function u, two-dimensional function u, with respect to its first variable x. Okay, one thing you notice is that you do not touch u. Okay, you are calculating partial derivative at point x and y. You take the limit when x is tending to 0, like you would do when you are defining this derivative for one-dimensional case, but you do not touch this second derivative. Okay. Similarly, you can define for du dy, and that is a limit where delta y goes to 0, and y. Now we don't touch x. Instead, we increment y by delta y minus u at x and y divided by delta y. That's definition of partial derivatives with respect to x and with respect to y. All right. So what is partial differential equation? Partial differential equation, that's what we're going to consider today. Partial differential equation, or PDE, is an equation that contains partial derivatives. Okay, partial differential equation for function u, multidimensional function u. So it has u is a function of at least two variables. Partial differential equation for such function is an equation that contains these partial derivatives. Just one example. Let's write that one example. For example, this is an example of a partial differential equation. Okay, this is an example of partial differential equation. This is an equation. We have partial derivatives of u with respect to x and with respect to y. In this particular case, this is a second order partial derivative with respect to x, and this is a second order partial derivative with respect to y. Okay. All right. So u is a function, as we said, of at least two independent variables. In this case, we call those independent variables as x and y. All right. So partial differential equations can also be linear and nonlinear, like ODEs. In the case of ODEs, this is an ODE which we consider dy dx is equal to some x, f of x and y, where function y depends only on one independent variable x. Here, we are looking for a function. The solution of this PDE is a function u, which depends on not one, but at least two independent variables. All right. So this can be linear. This can be linear when this equation is linear. This equation is linear when this equation is linear with respect to u and its derivatives. Okay. So there are different types of partial differential equations. There are different types, different orders, different dimensions. Number of dimensions may differ. They can be linear, nonlinear. Some of the simplest, but at the same time, some of the most commonly used type is linear second order partial differential equations. Okay, linear second order PDEs. Okay, and those equations we will consider in this class for the rest of this class. Okay, linear second order partial differential equations. There are other types, but the second order linear version is simple enough, at the same time widespread enough that we can consider in this class. Okay, so the most general form of linear second order partial differential equation is the following. Some function a multiplied by, this is just one example, This is, by the way, second order linear partial differential equation. It's just one example. Now I'm going to write some general form, the most general form of such equations. Second derivative of u with respect to x. So we are writing it for a function u, which is a function of two independent variables, x and y. Okay, this is the most general form. What is a, b, c? A is a function of x and y. So is b is some function of x and y. And c is also some function of x and I. They cannot be functions of u or derivatives of u, because in that case, what we would get, if this was a function of u, the derivatives of u, what would be is that possible or not? Okay, so I will write an equation which is like this. What's the problem? This is a nonlinear equation, right? This is a nonlinear equation. This is a nonlinear equation now. What I am writing is a generic form of linear equation, so by definition that cannot depend on u. Linear equation is an equation which is linear with respect to u or its derivatives. Okay, that's why this a's cannot depend on u. What about d? D can depend on x and y, also du dx, first derivative, and du dy with respect to x and y, and also u itself. Okay, so this is the most generic form. The most generic form. Okay, so this is the most generic form. Very good. So this is the most generic form. So it turns out, depending on the values of this a, b, c, we get different types of partial differential equations, second order partial differential equations. Okay, so we have to look at the value of this quantity, b squared minus 4ac. Depending on the value of those, we'll get different types of equations. Okay, so first possibility, this can be smaller than 0. This is a type of the equation. In this case, the equation is called elliptic partial differential equations. Elliptic partial differential equations. Elliptic partial differential equation. Example, let's give one example here. An example of this is the following. Second derivative of, let's say, temperature with respect to x plus second derivative of temperature with respect to y is equal to 0. This equation is called Laplace equation. Laplace equation in two-dimensional case. Of course, you cannot second derivative of t with respect to z if you have additional variable. So, what does this describe? What does this describe? As you can see, there is no dependence on time. There is no time derivatives. So, as you can guess from that, this kind of equation describes steady state solutions, certain steady state solutions. What kind of steady state? We'll discuss in a bit. Steady state situations. For example, as an example, let's consider three-dimensional version of the Laplace equation. Okay, so let's apply it to this room. This describes steady state. T is the temperature. X, Y, Z are spatial coordinates. Let's say this is X, this is Y, this is Z, for example. So what does this describe? What is the solution of this equation? What's the meaning of the solution of this equation? Again, there is no time dependence. It's a steady state. So when we can approach it? For example, we have a heating system, right? There is an air, warm air propagating in this room, warm air produced by air conditioning. Then we have windows and we have colder outside. So there is some kind of heat balance. On one hand, this room is being heated. On the other hand, some heat is leaving this room through window, for example. Okay, when you just switch on the heating, temperature starts increasing, right? But at some point, you reach a steady state. It doesn't increase anymore. Okay, for example, you come in the morning here, it's cold, you switch on the heating, and temperature slowly raises, and at some point you reach a limit, you reach a state where heat which you are putting in this room becomes equal to the heat which is leaving this room. In that case, time dependence disappears. Initially, when there is no balance, you start heating, there is a lot of heat is being produced, room is slowly going up temperature, but at some point you reach the constant temperature. That is steady state. And that's governed by this equation. You put correct boundary conditions, let's say, what is the temperature on the floor, what is the temperature on the window, or what is the heat flux at the boundaries, and you solve this equation, and the solution of that equation is that distribution of the temperature in this room. So it describes that situation, steady state temperature distribution, for example. But generally, it doesn't need to be only temperature, it can be other processes, but one example is this temperature distribution. All right, so that's the one example. Second possibility is when it is equal to 0, and that equation is called parabolic equation. Parabolic equation. And for example, an example of that equation is heat conduction. An example, simple example, derivative of the temperature with respect to T time is equal to some K prime, second derivative of T with respect to X. Okay, this is an example. You can see here now we have a first derivative with respect to time. Here is second derivative with respect to X. What does this describe? For example, this describes the following situation. Suppose you have a, I don't know, thin object, one-dimensional thin, one-dimensional object, and this is your X coordinate. What you can do, maybe you can start heating one side. You can start heating one side, putting some heat into one side, warming it, one side of it, which means this side becomes hot, and then heat starts propagating in this direction. Heat starts propagating in this direction. So there is some change of temperature in time. First it was hot here, but then everything starts becoming more and more warm, right? So some heat moves in that direction. That's a heat transfer, and says, which is a solution of this equation in one-dimensional case. Okay, this is a one-dimensional heat transfer. There is a time dependence because the temperature changes in time. Whereas before Laplace equation, there was no change in time. It was steady state. So that's the difference. So it describes. So one reason why these equations are classified in this way is because they describe completely different situations, and they have completely different, significantly different mathematical properties. All right, final piece. What if this guy is larger than 0? This b squared minus 4ac is larger than 0. Can anyone guess what is the name for this case? Hyperbolic equations. Hyperbolic equation. Hyperbolic equations describe wave phenomena. For example, light. This light from this bulb is propagating in space. That propagation is described, for example, by a wave equation. For example, in the simplest form is this: second derivative of u with respect to x is equal to 1 over c squared multiplied by second derivative of u with respect to time. Okay, c is the propagation velocity of that wave phenomena. Okay, so that's the classification. Now let's start discussing in deeper, starting with these elliptic equations. Okay, let's describe elliptic equations more deeper. Okay, first we will derive. Let's first derive this equation. Let's derive this equation first, and then we'll discuss how to solve it numerically. We want to derive Laplace equation. Okay, let's consider a rectangular plate. Uniform rectangular plate. I'm going to draw it here. So this is our plate. This is our plate. Okay, let me draw it slightly differently. Let's say it goes this way. All right, so let's say this is my x coordinate, this is my y coordinate, and let's say that this is my z coordinate. Let's say that this has a thickness of delta z. Okay, rectangular plate. And I want to derive this equation, this steady state temperature distribution for this plate. Okay, so I'm going to look at small piece of this plate. Let's say this piece in somewhere in the middle. Okay, at steady state, when temperature is not changing, if you look at this plate, this small element, small plate element, the amount of heat entering this plate should be equal to the amount of heat which is leaving this plate. Otherwise, temperature would change. For temperature not to change, the amount of energy we are putting in should be equal to the amount of energy we are putting out. So let's say that this is a point, let's say x and y. So from this side, you are putting some energy. Let's call it qx at point x. And from this side, some energy is leaking out. Let's call it qx at x point x plus delta x, because this is a point where x plus delta x. So the thickness of this element, plate element, has a volume v equal to delta x, and this y dimension is delta y and delta z. Okay, this is this dimension, delta x, delta y, and delta z. Okay, that's the volume. So qx is a heat, which is heat flow coming in this direction, and qx plus delta x is a heat flow at this end of this guy. Okay, so that's heat in the horizontal direction. Now let's look at the vertical direction. There can be heat coming in. Let's call it qy at y, and there can be heat which is going out. Let's call it qy y plus delta y. Okay, in order to be a balance, in order for temperature not to change, what is coming in should be equal to what is coming out. Okay, so let's add them up together. First of all, let's clarify one quantity. That is, for example, qx. Okay, so qx is a flux, heat flux at point x. Heat flux at point x. From heat flux, how we calculate the total amount of heat transferred in delta T. Total amount of heat, or energy transferred in delta T time through this surface, with area delta A. Okay, so we have a surface. Let's say this is a surface of area delta A, and there is a heat flux, which is qx. There is a heat flux coming right here. So what is the total energy that passes through this region in delta T? What is that? Total heat. Let's call it Q capital. Flux total is just flux multiplied by area multiplied by time, right? So it's just Qx delta A multiplied by delta T. Okay, that's the total energy. That's the total energy which you put in at delta T through a surface delta A. Right? Okay, now let's look at the total energy which enters or exits this plate element in time delta T. First, let's look at the heat which enters through this surface. So that will be Qxx delta T multiplied by the area. The area is delta Y multiplied by delta Z, right? The area of this element is delta Y and delta Z. Okay, plus now heat enters from this side. That is Qy at point Y multiplied by delta T, and the area, what is the area here? Delta X multiplied by delta Z. Delta X multiplied by delta Z, and that should be equal to what is leaking out, which is Qx at point X plus delta X. Now we are looking at this surface, multiplied by delta T, delta Y, delta Z, plus Qy at Y plus delta Y multiplied by delta t. Of course, now we're looking at the heat leaving through this surface. Multiplied by delta x and delta z. All right, what we can get rid of? I have delta t everywhere, so I can get rid of delta t. I have delta z everywhere, so I can get rid of delta z. What is left is qx delta y, qy delta x, qx x plus delta x multiplied by delta y, and qy y plus delta y multiplied by delta x. All right, I can group several terms together. I want to group this one and this one together, and this one and this one together. So what do I have? I move this guy to the left-hand side. I have qx minus qx x plus delta x multiplied by delta y, and that is equal to qy y plus delta y minus qy at y multiplied by delta x. I'm going to divide by delta x multiplied by delta u, and then I take the limit where delta x and delta y go to 0. I have this guy minus this guy divided by delta x, qx x minus qx x plus delta x divided by delta x is equal to qy y plus delta y minus qy of y delta x. No, delta y, sorry. All right, so if I take the limit where delta y and delta x are infinitely small, I get very simple equation. Second derivative of qx with respect to x. No, not second derivative, first derivative, of course. Plus second derivative of qy with respect to y is equal to 0. What I did is basically I move this guy to the right-hand side, so everything becomes plus. Okay, so we are not still there. We are not still there. We need an equation for temperature. So qx, flux in the x direction, can be expressed through the derivative of t, dt dx. Okay, this is a Fourier's law for heat conduction. We can use this equation, where this coefficient is a coefficient of heat conduction, heat conductivity, coefficient of heat conductivity. Okay, qx is related to the derivative of x. Similarly, qy will be then k prime dt dy. Okay, so I can put these two expressions for qx and qy to this equation, and I get the Laplace equation. Second derivative of t with respect to x plus second derivative of t with respect to y is equal to 0. I obtained this Laplace equation. All right, very good. All right, very, very good. Slight variation of this Laplace equation is a situation, let's say, when we have a heat source somewhere here. Someone is heating this region, for example. We still have a steady state, but someone is heating that region. Or someone is cooling that region, in which case we say there is a heat sink. In the first case, when someone is heating that region, there is a heat source. In that case, instead of 0, we have some function f of x and y. That characterizes that heating or cooling. And this equation with this function f of x is called Poisson equation. Okay, very good. We derived this equation. Next task is to solve this equation. Let's now solve this equation numerically. So I want to solve this equation. Second derivative of t with respect to x plus second derivative of t with respect to y. Okay, so I want to solve for this rectangular plate. I have a rectangular plate on xy plane. This is my x-axis. This is my y-axis, okay? And let's say that boundary condition. What about boundary condition? Let's say that we have a fixed temperature at the boundaries. Fixed temperature at the boundaries. Okay? Which means that we keep the temperature, this boundary, this boundary, this boundary, this boundary, to be fixed and equal to some value. All of them do not need to be equal to each other. Maybe temperature here will be different than the temperature here. but it's fixed in time. It doesn't change with time. Okay, we have that situation. How do we solve this equation now? By the way, when you have fixed boundary, fixed temperature, fixed T as a boundary, if you have this kind of boundary condition, what is the name for that kind of boundary condition? It's called Dirichlet boundary conditions. Okay, great. Now let's solve it. How we can solve it? The simplest method we can solve is through finite differencing. Okay, finite differencing. Finite differencing. For which we first represent this plate as a sequence of points, sequence of fixed discrete points. So it's a grid of discrete points. Okay, so we have instead of continuous plate, we just look at specific points in this grid. Let's say that along x-axis, this is my point 0, 0, and this is my point where I equal to 1, 2, and so on, n plus 1, n plus 1. Accordingly, along y-axis, I have another index. Let's call it j. Here, j equal to 1. Here, both I and j are equal to 0 at the origin, at this point where both I index and j index are 0. I index shows me the number of index of the point along x-axis. Okay, so this one would be, what is the index of this point? It will be 2, 1, right? I equal to 2, j equal to 1. So I come up with a sequence of points and I index each point. Each point has an index, okay? And I can define temperature everywhere. I call it Tij, okay? Let's say this is a point ij. At that point, temperature is Tij. So instead of temperature everywhere, I just look at the grid of discrete points, And I write this equation, I want to write this equation at those discrete points, okay? To be specific, let's say along y, where I have n plus 1 points, Zeros and n plus 1 correspond to boundaries, or I equal to n plus 1 or I equal to 0 correspond to boundaries, okay? So I have this grid of points. Okay. Next, I need to approximate this derivative. Second derivative of t with respect to x at point I and j through finite differencing will be just ti plus 1 j minus 2 tij. I'm using the centered formula. Plus 2 I minus 1 j divided by delta x squared. By the way, the distance here is delta x, and it's equidistant everywhere. Similarly, here, the distance between subsequent points, neighboring points, is delta y. The same thing I will do for the derivative of t with respect to y at point I and j will be just ti j plus 1 minus t I j plus t I j minus 1 delta y squared. All right. So I have a finite differential approximation for this guy and for this guy. So the only thing left to do is to put these guys here, and let's see what do I get. All right. So I put this expression and this expression to this equation, and what do I get? I'll just write the final formula. I get this kind of formula: ti plus 1 j plus ti minus 1 j plus ti j plus 1 minus 4 ti j is equal to 0. I forgot one term, I think. Yes, I forgot one term. Let me add that term quickly. Tij plus 1 plus, I forgot this term, Tij minus 1 minus 4Tij is equal to 0. Okay? So why do we need this equation? We write this equation for every point, for every interior point, for Ij corresponding to every interior point. Then we get a system of equations, let's say, in simple case, for example, this is my plate, and I have 4 interior points. Okay? If I write that, so this will be 1, 1, 1, 2, 2, 1, 2, 2. Indexes of these points, okay? And these are boundaries. So this point would be 2, 0. Sorry. No, of course not. This will be 1, 2, and this is 2, 1. This point will be 1, 0. This one will be 2, 0. This will be 3, 0, and so on, so on. But unknowns are t's at these points. So I write this guy for these 4 points. For I equal to 1, j equal to 2. For I equal to 2, sorry, first I equal to 1, j equal to 1. Then I equal to 2, j equal to 1. Then I equal to 1, j equal to 2. And I equal to 2, and j equal to 2 at these 4 points. When you have only 4 points. We do not need to have only 4 points. There can be more than 4 points, but for simplicity, let's say that for the moment there are only 4 points. So I write this equation. First will become t21 plus t01 plus t12 plus t10 minus 4t11 is equal to 0. Here it becomes t31 plus t002 plus t13 plus t11. Nope, I made a mistake. 3, 1, this is 1, 1. Two is 0 minus 4t21 is equal to 0. Now for this case I get t22 minus t02 plus t13 plus t11 minus 4t12 is equal to 0. And finally for this case t32 plus t13 plus t23 plus t21 minus 4t22 is equal to 0. All right, so I wrote this formula for all the points, for all the interior points here. So what are the unknowns here? Unknowns are t11, t12, t21, t22. Okay, 4 unknowns. So what about these guys? What about this guy, this guy, this guy, this guy, this guy, this guy, and this guy? What about those? And this guy. What about those? Where do I get those guys? These are boundary condition. T01 is this point. And boundary at the boundaries, by definition, by construction, or in this problem, temperature is given. Okay, those are given. So the only thing we don't know is that these guys, 4 unknowns. We have 4 equations for 4 unknowns. So we have a system of linear algebraic equations. We know how to solve them. One common way of solving them is through Gauss-Seidel iteration method. Gauss-Seidel iteration method. Okay. Specifically, from this expression, I find Tij. Tij is just 1 over 4 Ti plus 1 j plus Ti minus 1 j plus Tij plus 1 plus Tij minus 1. Ti plus 1 j, Ti minus 1 j, Tij plus 1, Tij minus 1. All right, we use this as iterative scheme, okay, for Gauss-Seidel iteration. So that's one common way of solving this equation. Sometimes this method of solving this equation is called Liebmann method. Liebmann's method. Okay, and that's all I wanted to say today. Okay, I have 1 minute. Questions? Very good, very good, very good. Delta y is equal to delta x. We made that assumption here somewhere. Otherwise, they wouldn't disappear. Delta y and delta x are equal to each other when we derive that equation. Very good point.